Good morning, respected faculty members and audience. I, Dinesh Prachapati, have been pursuing PhD under supervision of Professor K.D. Mandal, Department of Chemistry, IIT BHU Varanasi, Uttar Pradesh, India. Today I am going to present the PACC FMA 2022 symposium on the topic of preparation and characterization of bismuth yttrium doped BCTO ceramic. So this PPT contains many uh, many uh, things which are related to the dielectric properties of the ceramics. So, in introduction parts, in the modern age of science, there is a continuous demand for miniaturization of electronic devices such as cell phone, digital camera, notebook, computer, TV, etc. There is a continuous interest to develop a capacitor material with high dielectric constant and low dielectric loss for application to microelectronic, microwaves, memory, and capacitance-based energy storage devices. So here, the requirement for ideal capacitor material, there are various factors which is responsible for the requirement of an ideal capacitor material. First is high dielectric constant. Second must be low dielectric loss, and the ceramic should be high thermal stability. And fourth one is no variation in dielectric constant with temperature. And fifth one is no variation in dielectric constant with frequency. So perovskite, what is perovskite? Perovskite uh, is in general formula AbO3, where A and B are metal cations and the metal cation, where metal cations. The larger A cations occupy 8 corner positions, heavy coordination number 12. B ions in the body center position, having coordination number 6, and the oxygen ion occupy the center of 6 faces. The cubic structure often distorted to tetragonal rhombohedral orthorhombic symmetry. The structure of the crystal is generally determined by the a factor which is known as a tolerance factor. The formula of tolerance factor is T is equal to Ra plus Ro upon under root in bracket Rb plus Ro bracket close, where T is a tolerance factor and that describes the range of relative size for which the perovskite structure is stable. If T is between 0.95 to 1, then structure of the crystal will be cubic. If T is in between 0.75 to 0.9, then crystal will be orthorhombic with non-ferroelectric properties. If T is greater than or equal to 1, then it will be hexagonal. If T is less than 0.75, then it will be then compound doesn't crystalline in perovskite structure at all. Currently, the used capacitor material is BaTiO3 and RPB Mg1 by 3 and B2 by 3 in O3 as a capacitor material. This material have dielectric constant is from 1000 to 20,000, and dielectric loss is in between 0.02 to 0.2. But the problem with BaTiO3 is it is unstable and shows phase transition. It shows rhombohedral structure at minus 90 degrees centigrade, but it converted into the orthorhombic at minus 50 degrees centigrade, and again it converted into the tetragonal at 130 degrees centigrade, and again it converted into the cubic. Means this shows the as the temperature increases, the structure of the crystal will also change changed. Hope the dielectric constant is highly unstable with temperature, and it is not suitable for the use at high temperature. But and also the problem with lead related perovskite, because lead is a toxic in nature, so it is not eco-friendly. So these are the perovskite materials of general formula in three types, and these perovskite material have different application in the different field. such as BATI3 is used in the multi-layer capacitors, and we can say here GDFEO3 is also used in magnetic bubble memory, and the lots of perovskite material have individual application in the various field. Now the ACU3TiO4 type materials has been fascinated much more attention in the field of microelectronic device for the application because of its very high dielectric constant. When E is replaced by the calcium, then it is called CCTO. The crystal structure of CCTO is cubic, lattice parameter 7.391, and space group is IM3. First of all, the dielectric behavior of CCTO is observed by the Subramaniam in 2000, and Subramaniam also found very high dielectric constant of around 10 power 4 to 10 power 5 at room temperature. Since CCTO ceramic have been considered as an interesting material because of their high dielectric properties and have been used for the applications such as metal insulator, semiconductor, capacitor, and micro dip integrated circuits. CCTO material shows multiferroic properties at room temperature, such as data storage, optical utilization in visible light region, and snaps-like function. The BCTU, which is similar to the CCTO, that is isostructure relationship between them, has been and also has been documented in the literature. Young et al. Employ to synthesize the BCTO by solid state reaction methods and found it a very high dielectric constant of approximately 3.3 into 10 to the power 5 at 1 kilohertz. In my laboratory, Pooja et al. Also synthesized the same material, that is BCTO, by another route that is called semi-wave route, and it has also found very high dielectric constant of 2.9 into 10 to the power 4 at 3 to 3 Kelvin and 100 Hertz. But the dielectric loss of this BCTO ceramic synthesized by semi-wave route is found very high, that is approximately 10.0 at 1 kilohertz. So this high dielectric loss of the BCTU have this had dielectric loss of the BCTU, which is not make BCTU for suitable for various applications. The unit cell of CCTU. The unit cell of CCTU means what is the what means the the calcium in CCTU. The calcium occupied 8 corner of the cube and body centered, having coordination number 12 icosahedral geometry, and 6 copper ions are situated at the six face center and 12 A center, having coordination number 4 square field, and 8 titanium ions sit at the center of the TiO6 octahedral facing each other with bridging copper atom bonded to oxygen, having coordination number 6 and octahedral geometry. The structure of the CCTO is BCC, and the unit the dimension of the BCC is 7.391 angstrom. So this slide represents the how the 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 theory that affect the high dielectric that affect the origin of high dielectric constant. There are two theory. First is intrinsic, second is extrinsic. In intrinsic, can be divided into the two parts. Means the material will be polar, should be polar, and B, the local dipole moment associated with off-center displacement of titanium 4 plus ion. In extrinsic material, the first it is also divided into two parts. First is polycrystalline, means material should be polycrystalline, that is semi-conducting grade and insulating grade boundary. and electrically heterogeneous. Internal layer barrier capacitance, which is responsible for the high dielectric constant. D is single crystal domain and its domain boundaries. Objective and synthesis. There are few research have been done in the BCTU ceramic by doping or substitution of metal ion, but yttrium, but yttrium doped or substitution are very few study available. Following sample was to be synthesized by semi-wet route, which is in short form it is called as a BYCT. This is the experimental procedure and the way in which we have synthesized the materials. This slide shows the flow chart of the synthesis of ceramic material. First of all, we have taken the stoichiometric amount of metal nitrate and metal acetate in a beaker, in which water has already, and the separate solution of citric acid was also added in the solution and heat the whole solution on magnetic steroid for 24 to 30 hours at 970 to 80 degrees centigrade. After 24 to 30 hours, we have obtained the dry material which undergo grinding process to obtain the fine powder. The fine powder mix undergo calcination process at 800 degrees centigrade for 6 hours. The obtained calcined powder mixed with 2% of PBA solution, and to remove the PBA solution from the mixed PBA calcined powder, the material heated into the calcined furnace at 500 degrees centigrade for 3 hours. The obtained material undergo pelletization with the help of pelletizer machine, that is hydraulic pressure, by applying 4 to 5 ton pressures. The obtained pellet undergo sintering process where the densification occurs. The sintered pellet undergo for analysis of XRD, means where we have confirmed the material is formed or not. If the material is means phase is formed, then it will go for further characterizations. That is transmission electron microscopy, selected area electron diffraction, scanning electron microscopy, energy dispersive X-ray spectroscopy, X-ray photoelectron spectroscopy, and last one is measurement of dielectric and electrical properties. So phase formation of the ceramic were also confirmed by the XRD pattern, where all the were correctly matched with peaks were correctly matched with the JCPDS card number 460725. In XRD pattern, there are several peaks of different 2 theta values. Since in this XRD pattern, each peak have indivisible crystallized size. So the average crystallized size of the BYCTO ceramic was calculated by the calculated 62.3 nanometer. Tame and set. Figure 1 shows the tame image of the BYCTO ceramics, and figure B shows the set pattern of the BYCTO ceramics sintered at 900 degrees centigrade for 8 hours. In figure A, the particle are looks nearly spherical types, and each particle have different particle size. So the average particle size is calculated by ImageJ software and found to be in the range of 55 plus minus 7 nanometers. In figure B, and this is the set pattern of the BYCTO sintered ceramic. In this in this set pattern, we have seen the bright spot, each spot having indivisible HKL value that confirm the material, confirm the ceramic are polycrystalline in nature. Same and EDX. Figure A shows the same scanning electron microscope image, and B shows the EDS image of BYCTO centered ceramic uh, at 900 degrees centigrade for 8 hours. From figure A means in same image, the particle are looks in polygonal types, and we have also seen the porosity in the material, where which is due to the evolution of which is due to the evolution of some substantial gases during citrate nitrate combustion when we have synthesized the material. The average grain size of the uh, of the synthesized BYCTO ceramic was found to be 0.783 micrometer. Figure B represents the EDS image of the BYCTO ceramic centered at 900 degrees centigrade for 8 hours. Where from figure B we have confirmed the element bismuth, oxygen, copper, yttrium, and titanium are present in the material, and the purity and the stoichiometric amount were also verified by this EDX spectra. This figure shows the XPS spectrum of the BYCTO ceramic. Figure A, B, C, D, and E represent the XPS spectrum of bismuth, yttrium, copper, titanium, and oxygen. In figure A, we have observed the two peaks uh, of around 164.01 electron volt and 158.79 electron volt having corresponding term symbols. That indicates the bismuth present in the material in plus 3 oxidation state. In figure B, the X-phase spectrum of yttrium 3D, where we have observed only one peak around 158.78 electron volt. That indicates the yttrium present in the material in plus 3 oxidation state. Figure C presents the specific spectrum of copper 2P. In this spectrum, we have observed several peaks, some satellite peaks and some peaks which around 953.70 electron volt and 933.7 electron volt having a corresponding term symbol that indicates the copper present in the material in plus 2 oxidation state. The figure D represents the X spectrum of titanium 2P. In this spectrum, there are several peaks along with satellite peaks. Each peak has individual binding energy that indicates the titanium present in plus 4 oxidation state as well as plus 3 oxidation state. The plus 3 oxidation state of titanium in the material is maybe in the material occurred due to the evolution of occurred due to the oxygen vacancy during the sintering process. Figure E represents the oxygen 1s XPS spectrum of oxygen 1s. In this spectrum, we have observed three peaks. Around one is around uh, 5 to 9.48 electron volt that represent uh, the metal oxygen bond in the crystal lattice, and they peak around 530.87 electron volt that indicates uh, the 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 that indicates the peaks around 530.87 electron volt, which is due to the absorbed oxygen or hydroxyl group, and the peak around 532.77 electron volt is due to the oxygen vacuum. Dielectric studies of the BYCTO series. Figure A and Figure B represent the frequency-dependent dielectric constant and dielectric loss of BYCTO ceramic sintered at 900 degrees centigrade for 8 hours at a fused electric temperature. In this figure, we have observed the dielectric constant decreases with increasing the frequency and almost constant after 10 kilohertz. The decrement of the dielectric constant in the lower frequency region as well as dielectric loss in the lower frequency region is due to the space charge polarization. It is due to the mainly space charge polarization is responsible for the decrement of dielectric constant with frequency. Since in lower frequency region the charge generates more electronic polarization because it has more time to cover the long distance in the material and consequently dielectric constant increases. But in higher frequency region the dielectric permittivity doesn't change much more because of space charge polarization. Space charge no follow longer the external electric field means no charge accumulated at the interface of the uh, grain and grain boundaries. The dielectric constant and as well as dielectric loss was determined 610 and 0 uh, 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 and 0.9 0.92 at 307 and 1 kilohertz. Conductivity measurement. Figure A and Figure B represent the conductivity of the BYCTU ceramic with respect to temperature and with respect to frequency. Figure A represents the dielectric the conductivity of BYCTO ceramic with temperature. In this figure, we have seen the conductivity increases with increasing the temperature. In this figure, the conductivity can be fitted by Arrhenius equation. Sigma is equal to sigma naught exponential in bracket minus E oblique EA upon KBT bracket close. The activation energy for ionic conduction was found to be 0.212 electron volt, 0.209 electron volt, and 0.152 electron volt at 1 kilohertz, 10 kilohertz, and 100 kilohertz respectively. Figure B represents the frequency dependent conductivity at few selected temperature. From figure we have seen the conductivity increases as the frequency increases. Increases, but the conductivity uh, in lower frequency region follow the universal in lower frequency region uh, in lower frequency region that in lower frequency region uh, क्या region था मुझे याद नहीं। तो आप आगे बढ़ जाओगे follow the universal power law sigma s is equal to sigma naught plus a omega to the power s where s is the power exponent law whose value is lies between 0 to 1. The value of s was extracted 0.839, 0.806, 0.751 and 0.719 at 307 Kelvin, 367 Kelvin, 427 Kelvin and 487 Kelvin respectively. This indicates the frequency dependent of AC can be explained in terms of correlated barrier uh, Hoping model. So conclusion, BYCTO ceramic was successfully synthesized by semi-wet route. Single phase formation was confirmed by XRD. Same micrograph shows clear grain and grain boundary with average grain size in the range of 0.783 micrometer. Stoichiometry and purity of BYCTO ceramic were verified by the ATX analysis. The particle size of BYCTO ceramic by TEM studies was of 1055 plus minus 7 nanometer. The oxidation state of the element were confirmed by the XPS. Dielectric the constant and tangent law decreases with increasing frequency at various temperature. Last one is AC conductivity of the ceramic increases with increasing frequency obeying the Jancher power law. These are the reference. Thank you to all of you.